So it's my great pleasure to introduce Mike Hill. He will be giving the first of his 3 talks on equivariant and n-infinity operads.
Thank you. So you may have noticed, if you've ever seen me give a talk, that it's a little spontaneous. Of course, that's purely the performance aspect. I certainly plan ahead. That part wasn't the joke. But I was told that I had to give slides. So if it feels inorganic and wooden, just imagine that I'm a US government official. This is recorded, isn't it?
I sound like anything. So this should be fine.
I'm gonna save the, I assume, 7-second delay that they have in my video on for when I start swearing. But all right, that was my preamble. Let's get started. Oh no. Oh, my talk's over. All right, great, thank you. Okay, so what? Okay, here we go.
Don't hit the middle button.
All right, don't hit the middle button, don't stare right in the laser. Okay. So the main takeaways for my series of talks is that I want to first equivariantize everything. Obviously, in a workshop like this, I don't feel like I need to justify that claim. You've already drunk this Kool-Aid. But what I mean by the statement is anytime I have a diagram of objects, then I want to also include the possibility that the group acts on the diagram, not just all of the constituent pieces in the diagram. And I want to be able to do this in some sort of compatible way. So maybe I've got a G mod H worth of objects, and each of them is some kind of H object, and I want to think about intertwining those two things. So one theme to keep in mind as I go through this is exactly that. I want to do this. You're very familiar with these kinds of constructions. This is induction in representation theory. This is co-induction in representation theory. This is tensor induction in representation theory. They all get the same kind of name. And we're just going to end up spending some time. I don't know exactly when, because I don't know how long any of these talks is going to go for. But we'll spend some time staring at me, figuring out exactly what I mean by the statement. And the second that I want you to also keep in mind is that anytime I talk about some kind of structure or some kind of algebraic object, there's sort of 2 ways that I can look about it. There's a way that I want to call an internal form, and there's an external form. And the internal one, the structure tends to be encoded by something like, maybe I have a diagram of groups together with restriction and transfer maps, like a Mackey functor. The external version is I have a diagram of coefficient systems and then maps that externalize the transfers. And we'll see this a couple times in the multiplicative version. Very often, the external one is what's given to us by the operatic algebras. The internal one is the one that's often easier to actually do computations with. So it's helpful to keep in mind that I have these 2 different perspectives that I can play off each other. And so historically, the right-hand side, these are all named after people, even though Mackey didn't define Mackey functors, of course Dress did, and Tambara defined what he called TNR functors, and then we call them Tambara functors, ignoring his wishes. So you're gonna have to edit a lot. Just to warn. I see you're like literally texting them, stop recording. And those are the internal forms. The external ones are the so-called G-commutative monoids, and I think you know about it. So since I'm talking about operads, I want to start with work of Stasheff. And I also want to start with the fact that I spent probably an hour making that Tixie diagram. I know, it's gorgeous, you're welcome. Yes, thank you. But story of operads, at least the way I understand it, starts with a lot of work of Stasheff. And if you want to understand the question of when do I recognize that something is a loop space? How do I know what sort of structure shows up? And before Stasheff's work, there was somebody who actually identified this, and his name I'm blanking on, Sugawara. And then what had been known is stuff that like basically Poincaré told us, that I don't have an associative multiplication on loops, but the failure of associativity of the multiplication on loops is something that has a coherent homotopy that connects one to the other. And so what Stasheff noticed is that I can actually start to build a different way to understand the multiplication. I can instead parameterize the multiplication that I see by spaces. And here, I'm using these little intervals, or little one disks, and I'm describing that I've got embeddings of the interval, a disjoint union of n copies the interval, into itself. And this gives me a space. And as n varies, well, the space assembles into a bunch of structure. The key point that I want to make here is that a choice of embedding of the intervals, in this case, in my picture, I should, full disclosure, this one I drew by hand. There's like literally no way I could have gotten to like, literally no way. But given the embedding of three intervals there, there's a blue one on the left, there's a green one at the top, and a red one to the right. That gave me a sort of marking on the circle. And the circle, there's a blue part here that corresponds to this blue part. There's a green part here that corresponds to this little green part. And there's a red part here that corresponds to this red part. And then every part that's not in one of these RGB colored areas, then I would just crush down to the base point, and this gave me a map from a single circle to a bouquet of three circles. Maps out of a bouquet of three circles in pointed spaces is the same thing as a triple of maps. One from the red loop, one from the blue loop, and one from the green loop. So I've written down a map from one circle, let's assume that I've pointed that one as well, into a bouquet of three. Pre-composing with that map gives me a way to take three loops in my space and turn it into one loop in the space. So every embedding of three intervals in gave me a choice of multiplying three elements in my loop space. And with Stasheff noticed, and then also around essentially contemporaneously, Boardman and Vogt built a way to say this structure actually is determining everything about my loop space. If I have the coherent collection here, then I can do it. So what sort of things did I need to talk about the coherence? I need this composition. And composition's a little confusing in this sense. The way you should think about it is as I sort of drew them, I'm slotting intervals into others, and then I can slot intervals in and then further slot those in. And the composition is just that I can embed and then further embed. And I asked the composition be associative, which basically means if I slotted three ways in, I mean, I only drew sort of two nestings, but if I had like a layer up above, then the associativity matches your intuition. That if I did the first two slottings and then slot that into the third, that's the same thing as doing the second into the third and then slot in. So it's kind of matching the way we're thinking about it. And this gave me, now, as I wrote it, I had the three intervals here, the blue one, the green one, and the red one. And then into the blue one, I slotted in this gold one and this sort of purple one. And then you can't really see it. I don't know, maybe we would see it if you were actually watching this on the Zoom. But like down here, there's an itty bitty gold one. And I can't believe you can't see it because it's literally the width of my finger. And then next to it, there's a slightly bigger purple one. And those are embedded in the little blue one. It works better if you're the one giving the talk and you're standing right at the board, but you'll have to just trust me. So given this, I had a way to now say, take these four things and produce an embedding of the four into the one. And so this is a kind of composition or sort of a way that I'm describing how to further multiply my loops. And the last bit of structure I have is that I can permute the coordinates. And then they took the examples that Stashev had for associativity, essentially this one, and then Boardman and Volk had to describe higher loops, especially E infinity, and he parameterized this. And this gave us the notion of an operad, and since this is the equivariant community workshop, then I'm going to also put in a G action everywhere. My groups, oh dang. Talk's ruined. Threw me off my game. So all of my groups are going to be finite groups. A lot of what I say actually works in the compact Lie case. Every time I say, if you want to think about the compact Lie case, I only ever consider finite index subgroups, and then everything I say goes through mutatis mutandis. It turns out there are groups that are not finite or compact Lie. I will not consider those. So, here. Sucks to be you for finite groups. But so in this case, May sort of axiomatized what was witnessed and gave us also this really nice term, an operad. And here for G space, I got a sequence of G cross sigma n spaces. So that's my symmetric group on n letters, one for each natural number. So there's a particular element that I'm going to single out as an identity in O of 1. It's the identity for the composition that I then have also as part of my structure. Namely, I have exactly what we saw before, O of n cross OK1 and so on up to OKn, and the whole thing maps to O and the sum of these. And if I were writing this on the board, then I'd draw the canonical picture of a bunch of little boxes with a bunch of little inputs, and then I slot them together and I say, think about these as generalized functions where I take k inputs, and that's what O of k is parameterizing. So think about these as generalized functions where OK takes k inputs, and that's what it's parameterizing. The identity map that I'm choosing is just an identity for the composition. It behaves exactly the way you think it does. If I slot it in, it doesn't do shit. I told you. And then I expect, or I insist that the composition be associative. And so in exactly the way I described, sort of as a layered tree approach, it didn't matter what order I do my composition. Yeah.
Maybe you said, and I missed it, maybe a word about how, in what sense the map is supposed to preserve the G action.
Oh, no, I didn't say. Great, thank you. So everything inside is G equivariant. And the real question is, how does it interact with the sigma end action? And that's a little trickier.
So GX diagonal on the left-hand side.
Exactly, GX diagonal on the left-hand side, and then on the right-hand side is part of the data. And the sigma n action, I was deliberately avoiding saying, because it's a little complicated. I can sort of see what's happening from the fact that I should think of this as a decomposition of the set with this many elements into n blocks with this blocks of this size. And then I have a subgroup of the symmetric group on K1 up through Kn letters that reflects that decomposition. And that's sort of a way to think about the equivariant. That's actually one of the harder points that I'm gonna spend most of the time sweeping under the rug. But thank you for forcing me to be honest. Okay, so once I have an operad, then I can talk about operatic algebras. And in this case, I've got a G space X, I had some fixed operand O, and I ask that I have a bunch of maps On cross sigma n back to X that are compatible with composition. And again, I forgot to typeset that cross is actually supposed to be cross over sigma n. So that the symmetric group was acting on both pieces. It acted on X to the n by permuting the coordinates. It acted on O of n because that was part of the structure, and then I'm identifying those two things. So the prototypical example, and the one Natalie, I assume you're gonna spend a lot of time talking about this one, so sorry, there's gonna be overlap. The prototypical example is the little disks in an orthogonal G representation. So I needed the orthogonal to make sense of the word disk in this. And then just take D of V. You'll notice I'm using two different fonts for this. The script font, most of my operads are going to be written in the script font. And then the right-hand side, the non-scripted D, that's just the unit disk in the representation V. And there should have been another copy. Oh man, slides are not my friend. So again, I'm going to take embeddings of a bunch of copies of my disk, and I'll embed it into one copy of the disk. The identity is the fact that one copy of the disk embeds into one copy of the disk as the one copy of the disk. And that, it turns out, if you compose things with that, doesn't do anything. And then the key parts are, I just sort of slot disks into each other. That's the composition, just as I drew before. And the symmetric group action is commuting the disk coordinates that show up. So this gives me a really useful family of operands. Now, the whole game that I want to end up playing is really one of commutativity. And as I work through, I'll give this prototypical example, and I like this because I can gesture through it. And see me talk about related stuff. You've seen me do this using gestures. This is the it's creeping me out. So the little one disks is not path connected in the sense that if I do this embedding where there's the line that's standing in front of me, I'm not just sort of like putting my arms out to faith heal you. So clear the please do. No.
More money for the editor.
The entire budget is. What are we gonna do? Okay, so I have the line out in front of me, and then I've got two intervals given by my two hands. And when I embed them in this way, that's a distinct embedding than embedding my hands in this way. And actually, I physically know this because I can't reach this configuration from this configuration by just continuously moving my hands around in this plane, because my hands don't pass through each other. That I can push as hard as I like, and it gets painful fast, but like it doesn't actually realize what I want. So in fact, I have two distinct path components. This one, because as I really the only invariant that I have is, did I preserve the orientation of my two hands going in, or which I had with my hands reversed, or did I, well, in this case, preserve the orientation of my hands going in? If instead I did the little two disks, then I can do it. And this is one that we know from, in fact, from when the higher homogeneity spheres were first developed, this was Harevich, noticed that like pi 2 is abelian and all the higher ones are. It's exactly this statement that I can move the two disks past each other. I can rotate them around. I can say here by saying that as k grows, the little disks in R to the k with a trivial action of g, so this is actually still an equivariant statement, the little disks in R to the k becomes more and more highly connected. If k is 1, then this doesn't end up being path connected, that's what we saw. K is 2, it's path connected but not simply connected. K is 3, but you can guess the pattern at this point. And so one of the things that I learned is as I pass to infinity with k, then I write down a bunch of spaces, each of which have a free sigma k action, and they're all contractible because they were infinitely connected. So the contracted, this is the Boardman-Vogt definition of an E-infinity operad. It's an operad, I have a sequence of spaces. The symmetric group acts freely and all the spaces in the operad are contractible. So what this gives me, when I think about it, so what sort of structure to say, there's essentially a unique sigma n equivariant map from sigma n into O of n, if I have an E infinity operad. Because a sigma n equivariant map is by the fact that I'm mapping out of sigma n. A sigma n equivariant map is determined by where you send the identity, and it's just a non-equivariant map from where I send the identity. But I'm mapping a point into a contractible space. Maps from a point into a contractible space is a contractible space. So there's essentially unique sigma n equivariant map. That means that any choice of this, and there's kind of only one up to coherent homotopy, any choice of sigma n equivariant map from sigma n in gives me this multiplication map from x to the n, which is sigma n cross over sigma n with sigma n. I map that into the nth space of my operad using my map sigma n into E infinity n. I needed that map to be sigma n equivariant to be able to take that sigma n equivariant map, cross it over sigma n with x to the n, but now I just use the operatic structure map to take me to x. So I get an essentially unique choice of multiplication. The uniqueness gives me a ton here. It gives me associativity, it gives me commutativity, because the difference between my map, that was a choice of embedding sigma n in, and the map in the other order is just a different way of embedding sigma n in. But there's only one way up to coherent homotopy to embed sigma n in. So embedding it in exactly the thing. Now I'm doing this the one-handed version because I'm holding this. Embedding this in, this is an embedding of sigma 2 into my operad. I can coherently deform that into embedding this sigma 2. And I don't gain or lose it. So it's coherently commutative, it's coherently associative. And when I went to Peter May and said, we defined E infinity wrong for G operads, he very, very kindly took me aside and said, no. No. E here means everything. And so it is sort of matching. It's something that's coherently commutative, it's coherently associative, it's got all the things that we want.
Why did you think it was wrong before?
That's a great question. I'll get to that. Thank you. So now I spent a lot of time. I don't know when I started, and I don't know how many slides I have left. So it's an adventure for all of us. So I was talking about these little disks, but I'd only been using what happens with a trivial action as I worked my way through. So I want to now switch to allowing a non-trivial action, and then I start to ask, what do I get from this? What additional data do I get? Essentially answering Greg's question of how do I intertwine the action of the group with the operatic action? And then I want to see in particular what this does in the case of the little disks operad, because it gives me sort of an intuition for how these things can interact with each other. And then finally, what plays the role of E infinity, or why did I have the audacity to say to Peter that maybe we call it something different. I learned the error of my ways. Y'all know. Okay, so I want to switch now to think about things in equivariant homotopy a little more. And so I want to start with Elmendorf's theorem because it's one of those theorems that I've grown to appreciate more and more as I continue in this field. This also gives me a chance to introduce the notion of a coefficient system. And normally when people talk about this, if you read the Alaska notes, they only talk about coefficient systems of abelian groups. But really, it's kind of the fundamental object that you want to consider when thinking about equivariant homotopy. So I should talk about a coefficient system in any old category. In this case, I'm talking about a coefficient system of spaces. And that's just a contravariant functor from the orbit category into spaces. And I'm going to use top. Sometimes people use a script S to indicate this. I find that confusing because I also write a script SP for spectra, and I start to get I get distracted by that, and then I find myself rambling about it during a talk, and so I'm sticking with the old school. So. No. So here, what was my orbit category? The orbit category here is, I can think of it two ways. I can think about it as just take the orbits G mod H as H ranges over the subgroups of G, and consider all, those are my objects, and then take all equivariant maps between them. And that's giving it to me. Alternatively, or equivalently, I can think about this as the full subcategory of the category of finite G sets spanned by the transitive G sets. And so that's you can think about them in a lot of ways. They're sort of, it's all describing the same thing. But then I'm just using this sort of Yoneda embedding, given X, I got this functor. In fact, given a G space X, I really had a functor from all G spaces into top, but I can restrict it to just finite G sets, or I can restrict it further to these orbits. And what Tony told us is that this assignment that goes from my space X to my coefficient system, that was a functor from the orbit category up into top, that gave me an equivalence of infinity categories here. It took me from G spaces to functors from the orbit category into spaces. Now, as an aside, that witnesses the right-hand side as a pre-sheaf category of spaces. And then Dan Duggar showed that pre-sheaves of spaces on some category is the free infinity category on that. So if I want to understand homotopy colimits out of that, all you have to do is tell me the value on the orbits. So anything you want to do, if I want to understand like homology theories, cohomology theories, Duggar's theorem tells me a homology theory or a cohomology theory, that's just something that commutes with homotopy colimits into some nice category. And then a functor that commutes with homotopy colimits out of pre-sheaves is just a functor out of this. And so it's a very straightforward description. I find it really nice. Lurie calls this the infinity category Yoneda lemma, but it's also a theorem of Dan Duggar's. All right, so let's think about what this means for my little disks. If I had my little disk, so here, remember, this part is the embeddings of n copies of the disk in V back into the disk in V. Well, I didn't say what I mean by embedding, and you probably at some level thought like, oh, I know what an embedding is. It's just sort of any map that's like a, you can use diffeomorphism onto its image. And of course, that's not what I mean. Mm-hmm. What I mean is the one that you were actually picturing, which was I shrink a little disk and then I slide it over. So you were probably thinking of affine embeddings where I'm allowed to scale and I'm allowed to translate. And those are the only ones that I actually mean when I talk about embeddings here. And if you consider what happened to the origin, which is the one thing that's scaling invariant when I took my little disk, then that gave me a map from the nth space in my little disks in V to just the ordinary embeddings, now it doesn't matter, of n points into the disk in V. So I'm choosing these n points, and the group acts by, the symmetric group acts by permuting these endpoints, and the group G acted as it did on the disk in V. So I can think about this also as the configuration space of endpoints, as the ordered configuration space of endpoints in V. And the group acts because it acted on G, and then sigma n acted as it did. So I want to spell that a little in that if you give me a pair, G sigma, sitting inside G cross sigma n, then the way it acts on an embedding is by this kind of conjugation action. I acted by permuting the input coordinates using sigma, and then I just post-composed with the multiplication by G. And so if you've seen this, this is awfully like the way I put a group action on the set of all non-equivariant maps. If I gave myself two G spaces, then the space of maps between them inherits a G action. and I use the same kind of conjugation structure. So here, the way I'm defining it, I'm saying, give this one a trivial G action, and give this one a trivial sigma n action. And now each of these has a G cross sigma n action, and then this action I described here is the usual one on the space of maps. And so keeping that in mind says, oh, like the natural follow-up is, well, why did I choose the trivial things everywhere? What happens if I chose different ones? And like, that's the payoff. That's like the spoiler, that's where I want to go. So when I think about the action, again, I want to take, I hate doing this, but I want to think about these G cross sigma n spaces from this Elmendorf's theorem perspective. And it tells me, understand the corresponding functors on the orbit category. Well, let me pause here for a second, because if I had an orbit G mod H, then to give myself a map out of G mod H into a G space X, since the group is acting transitively, you just have to tell me where one of the points goes. And G mod H has a preferred element, namely the identity. Like, I don't know, we like that element of a group more than any other. I know they're all the same, it's transitive, but some are more equal than others. And so I want to map I ask, where's the identity go? But the coset of the identity is also the coset of any element of H. And so wherever the identity element went, also every element of H had to go. So it had to land in a point that was fixed by every element of H. So this coefficient system of spaces is just a fancy repackaging of the diagram that says, to G mod H, assign the H fixed points. And if H sits inside K, then the property of being a K fixed point is harsher than being an H fixed point. So I have an inclusion of fixed points. So I want to play that game now here on my little disks in V. And the first thing I noticed is the symmetric group acts freely on the little disks. And that's just because when I think about it in the configuration space model, a different configuration space, the ordering is part of the data. So if I chose a different ordering, that's a different ordering. That's like literally the whole statement. So because of that, I don't actually care about the fixed points for the vast majority of subgroups of G cross sigma n. If I have just like a general product of groups, I know what the subgroups look like. There's a really complicated formula for this. I sort of choose a subgroup of the first, I choose a subgroup of the second, I choose subquotients of each of these and an isomorphism between them. So it's a pretty picture. I was able to describe it. You've never seen this before, like exercise. I don't know. Enjoy. But I don't care about any of the subgroups that actually intersect sigma n in a non-trivial way. Because the fact that sigma n acts freely tells me that if I have a subgroup that intersects sigma n in a non-trivial way, then the fixed points are automatically empty. So I don't care about those. The only ones I care about are the ones where my group gamma intersects sigma n trivially. And then it turns out all of these have a really nice form if you unpack what I just said in words into from the slide. Namely, if I have a subgroup that intersects sigma n trivially, then there's a subgroup of G, H, and a homomorphism from H to sigma n, such that my subgroup is the graph of that homomorphism. And so because that, people sometimes call these graph subgroups. They're graphs of homomorphisms from a subgroup of G into sigma n. Now, if you give me a homomorphism from H into sigma n, that's the same data as giving myself an H set structure on the set of n letters. So there's a dictionary that says graph subgroups correspond to a choice of subgroup of G and an H set structure on the set 1 to n. And if I consider things like graph subgroups up to conjugacy, then the up to conjugacy part says I take conjugate subgroups of H and isomorphisms of H sets or corresponding groups. So I see this dictionary that translates between the kinds of subgroups I care about and these H sets. And so using this, I can understand what happens from the various fixed points. So if I have a graph subgroup, and as I said, a graph subgroup corresponds to this finite H set that has cardinality n, then I can understand the fixed points in my configuration space. That's the same thing as embedding my finite H set. Oh, that should have been an H equivariant embedding, excuse me. It's an H equivariant embedding from T into V. That little G should have been a T. And the way to think about this is to think back to that description I gave of how did G cross sigma n act. And I said it looks like this conjugation action. Now, if I had my graph subgroup, then G is acting by moving the pieces around. And sigma n is acting by permuting the slots. And then G acts by permuting the images. And so what I'm doing is I'm permuting the slots by the inverse of the homomorphism, so that rearranges them according to H. And then I multiply according to the same H. So I'm rewriting, I'm permuting my coordinates, and then I'm mapping those in and acting again. So I undo the permutation and then redo it. And that's how I'm picking out these fixed points. But this really is, it's not a difficult observation, but it's a really key one. That the various fixed points that show up as I'm doing this exactly correspond to embedding not a set with a trivial action in, but a set with a particular H action. And the kinds of sets that show up correspond to what are the ones that this has fixed points for or not. And because of that, once I knew that I could get this gamma in, then I can play the exact same game I wrote on this slide with E infinity. A choice of gamma fixed point, so this is non-empty, a choice of point here corresponds to a map G cross sigma n mod gamma into my operad, because that's what the sort of Elmendorf story tells me. Maps out of an orbit is the same thing as a fixed point. But then now I have a map, G cross sigma n mod gamma into the nth stage of my operad, and that map was G cross sigma n equivariant. So I can do the same thing, cross that map over sigma n with x to the n. That gave me the equivariant space of maps from my finite G set T into X, and I send that back to X. And the collection of such maps is given by this embedding space. So I see now not just a multiplication, and this space in general isn't going to be contractible. So I have whatever topology of this space looks like, but for every point in this, I have a kind of twisted multiplication. Here, it's just the cardinality t-fold power of x, but I'm allowing myself to permute the coordinates. Let me look at an example. And the example I want to do is the C2 equivariant case and C2 equivariant loop spaces, where I have two that I can think about. I always want them to be pointed so that threw away the third circle you might have been thinking about. And the two I want to consider is I have the circle with a trivial action. That's entirely in blue. In fact, in this and the next slide, all of the fixed points are color-coded blue. If you can't see blue, or if you can't see blue because of this, trust me, they're color-coded blue. This whole thing is fixed, and that's an action of C2 on a circle. For this one, the action of C2 is non-trivial. These 2 points are fixed, and these two arcs were swapped. So this is the unit sphere in the complex numbers with complex conjugation, or if you prefer, it's the 1-point compactification of the sign representation. And associated to these, I have loop spaces. The leftmost one gives me the ordinary loops on a pointed C2 space. The right-hand one gives me the so-called signed loops on pointed C2 space, and that's kind of weird. And it's kind of weird exactly because these loop spaces are controlled by different versions of the little one disks. This one is controlled by little one disks in the trivial one-dimensional representation. This one's controlled by little one disks in the sign representation. So I have to understand what kinds of things embed, what kinds of finite C2 sets embed into the sign representation as opposed to into the trivial representation. And so this is not Tixie. This was embarrassingly a long time to draw by hand, given the quality. So here's my sign circle, and I'm just gonna get the punchline rather than the embeddings. I have a couple of things I can do. If I went to the right, that corresponds to a kind of embedding where I just sort of crushed the 2 points, the 2 blue points to 1. And this corresponds to the embedding of the C2 set, C2, into the sign interval. Because remember, the sign interval, the group acts by swapping the 2 pieces. And if I embed C2 into something that swaps the 2 pieces, well, the 2 points of C2 swapped, and their images swapped. So it actually gave me a nice embedding. If you want a concrete thing, it goes in as ±1, say. And the group acted by swapping this. That was this direction. And you see there's a little gray arrow indicating that these 2 copies of the one sphere got flipped. So this wasn't a copy of S1 wedge S1. This was a copy of C2 plus smash S1. Over here, I also marked these 2 little purple crosses. And this is an embedding now of 3 points into the of 3 points in, and the 3 points sort of went in as take a little tiny symmetric interval about the origin. That's one of my fixed ones, and then to a copy of C2. So this was a disjoint union of C2 with 1 point mapping into the signed interval. And that gave me this kind of weird thing where here I had C2 plus smash S1 wedged with a copy of the signed loops. So maps out of this is what the operad was describing for me. It gave me a map out of this twisted version of loops X cross loops X. This is maps from C2 into loops X. This is maps from C2 disjoint union point into loops sigma X. And I have these kinds of, they're not really multiplications, because the multiplication, the source and target are essentially the same thing. These are sort of twisted versions of that multiplication. And it's important to note that here, for a general signed loop space, there actually isn't a multiplication. I just have this kind of twisted one. But if I unpack what this does in the algebra, again, I want to think from this sort of Elmendorf perspective, then I have an ordinary loop space if I forgot all of the equivariants. But when I remember just the underlying thing with it, then the group was acting by, it was swapping that circle. That's the usual inversion in the loop space. And the inversion in a group is an anti-automorphism. It's an isomorphism between the group and its opposite. And so here I have a C2 action on the loop space that's acting as an anti-automorphism. I also have an action of this group, loops X, on the fixed points, and I have a particular choice of point in the fixed point. So it's like the analog of an E0 algebra. Like an E0 algebra, there's no multiplication. I have a choice of point that's remembering that I had a unit, and that's what I'm seeing in this other part. So I can think about this, it's a map from the underlying to the fixed points that's kind of, in some weird, loose way, additive, and that's the prototype for a transform. So I'm starting to see all of the structure that I want in equivariant homogeneity become additives. All right, So I want to get to n infinity, and I think I have time to do this. So what I'm going to do is I'm going to say, all right, let's copy the key things that I wanted from E infinity, namely the contractibility, the fact that there was a unique space, and hybridize that with the fact that these little disks in V had nice fixed points for various kinds of graph subgroups. And so I'm just going to choose that as my definition. I'm going to have an operad in G spaces, and I'm going to ask that sigma nx freely, that's what I was seeing in all the examples, and there's nice things I want that. And then I also want that the fixed points are always, for any subgroup, they're always either empty or contractible. That's my sort of analog of the E infinity part. And then I also want that the G fixed points are always contractible. So to say that fixed points are either empty or contractible is to say that I have what's called a universal space for a family of subgroups. If I have non-empty fixed points for some group, that forces non-empty fixed points for any conjugate, because the fixed points for conjugates are always isomorphic, and it forces non-empty fixed points for any subgroup of it, because fixed points for a big group is a harsher condition than fixed points for smaller. So the collection of things for which the fixed points is non-empty, or in this case is contractible, is some family of subgroups that sits inside G cross sigma n. And I'm insisting in the third point that that G itself always sits inside that family. All right, so some examples. If I have a universe, before I was sort of, I never actually said how big my representations were. I just said they were orthogonal representations. So you were probably thinking finite, and that was a deliberate obfuscation on my part. But it worked basically the same way if I allowed them to be infinite representations. If I ask that they be instead a universe, so that means the trivial representation sits inside there. And if a finite dimensional representation sits inside that universe, then infinitely many copies of it sit inside the universe. Those two things together guarantee that, in fact, the little disks in U is always an example of this, that all of those fixed point spaces, they look like configuration spaces of points in a big infinite dimensional Euclidean space, and those are always contractible. So they always give me contractible spaces. Another example is the linear isometries. So this is the nth space in this is isometric embeddings of the direct sum of n copies of U back into U. These are sort of the prototypes. And so the way that this connects to the algebra I described before is through this notion of what Andrew and I call an admissible set. And remember, subgroups, graph subgroups of G cross sigma n, those are the same thing as a choice of subgroup H together with a H set structure on the set of, I don't know, an H set structure on some finite set. And I'm a little, I don't know, squirrely about what the cardinality is here. So associated to, if I instead start with a finite H set, then there's a corresponding graph subgroup that's just the graph of the homomorphism from H to sigma n that classifies that H set. So I ask that the fixed points for that subgroup be non-empty. So in other words, be contractible. And that gives me it carves out for me a collection of finite H sets for each subgroup. I'm asking for this property that the corresponding graph subgroup fixed points are non-empty. And then some examples that show up, the condition that the G fixed points be that G be in the family, the G fixed points always be contractible. That corresponds to homomorphism from G into sigma n that took G to a point. And that is the homomorphism that classifies the trivial action on the n-point set. So that for any n, however many copies I had there, that's always an admissible thing. And then two things that are useful to work out. The first one I sort of sketched through earlier, that for little disks, something's admissible if and only if my H set embeds equivariantly into U. For linear isometries, admissibility is a harsher condition. If I tensor the permutation representation associated to T with U, that embeds in. And that's actually a really harsh condition. Permutation representations are kind of like regular representations. They're sort of like the blob. They just absorb everything, and then it's a really harsh thing to try and estimate. So one of the things Andrew and I showed is that if you have an admissible H set, then O structures an essentially unique twisted H multiplication from the maps from T into X back to X. So it's exactly like the E infinity thing had an essentially unique multiplication. Here, I have an essentially unique twisted multiplication for every admissible set. And if I did this for little disks, everything's admissible for little disks. And so I have any transfer that I would possibly want. Okay. So what I haven't used, but I've said in words a few times, is that the property of fixed points being non-empty is a family condition. So that gives me a bunch of constraints on admissibility in its own right. If a set is admissible for H, then the restriction to anything is admissible, because that's just passage to smaller subgroups. That also, I could use the sort of composition that comes from being an operad to force other things. And one of the things that we looked at when sort of defining these is that this actually gives you a purely combinatorial description for this. And so there's this interplay between these that I'm gonna quickly get to, because I know other people will use it, but I want to say in two ways. The first is, sorry, this is the most text-heavy slide, until the next one that's very text-heavy. So, an indexing system, as we defined it, is just this collection of subcategories, one for each H, and the subcategories are categories of finite H sets as H varies over all the subgroups of G. And then I ask for some properties, and each of these properties corresponds to features that show up in the operad. This one, sumANS, is the operad has a unit that I'm able to actually put the empty set in. Disjoint union is the operad has a composition. The restriction to subgroups, that was the fixed points were a family condition. So if I had it for a subgroup, I had it for smaller ones. Conjugation is fixed points are a family condition. And this last one, this self-induction, is kind of the weirdest, that if H mod K is in my category O of H, and I have T that's an admissible K set, then when I induce up T to H, that's an admissible H set. That's the twisted version of the composition. That's exactly the question that I wanted to avoid when Greg asked about the interplay between the symmetric group action and G. But having all of these, and I write down what the admissible sets did as H varied, it was exactly axiomatizing this that led to this structure. And so these form a poset under level-wise inclusion. And I drew out that poset, and this poset, you may recognize this shape. It's a pentagon. And it's not, yeah, it's a pentagon. It's also the first step in Stashev's associahedra. The very bottom one is an interval, which I'd also, I don't know, we've drawn a bunch of. But in this case, this is witnessing the fourfold associativity. And I drew the 5 possible indexing systems, much smaller than I hoped, that I see. And the way you should read this is the CP squared level, this is the CP level, and this is the underline. And so they're all the same. And what I want to stress here is I described sort of the generators, what orbits show up, because it's closed under passage to subobject, it's closed under disjoint union. You just have to tell me what the basic building blocks were, which orbits show up. And then I ask, is this closed under restriction? That's one condition, and if I have an orbit, G mod H, then induction from H to G has to be in there. So when I had the orbits G mod H, you can't necessarily see them, but you can see these little red arrows that go up. The black arrows going down, those are the restriction. The little red arrows that go up, that's just indicating that I had the corresponding orbit for this group. So here, I had the orbit CP squared at the top. Yeah.
This is the picture for G equals C.
Oh, yeah, this is for G equals CP squared. Thank you. This is for G equals CP squared. So here, I could record the entire picture. I don't actually need to see most of the internal structure. What I need to remember instead are the little red transfer maps that went up. And that records for me the same kind of data. And this was done by Ruben, and then I'm really glad that Dave stepped out, because otherwise all three of you would be here, and it's always funny to speak about who's work in front of them. But this is encoded in the notion of a transfer system. So John Rubin and then Scott, Dave, and Constanza gave this notion where I have a poset structure on the collection of subgroups of my group G. And then that would just satisfies these three little axioms. First, my poset structure is going to be given by an arrow. I'm thinking of the transfer. And then if I have a transfer from K to H, then K has to sit inside H. That's sort of matching intuition that the transfer should do. Second, it's equivariant for the conjugation action on the subgroup lattice. So if H transfers to K, K transfers to H, then the conjugate of K transfers to the conjugate of H. And then lastly, if K transfers to H and J sits inside H, then K intersect J transfers to J. So it's like an ideal under meet in the lattice. And what this forms a poset under refinement, and this poset of transfer systems is isomorphic to the poset that Andrew and I considered. So you can translate between the two of them. And the dictionary is exactly the one that I sort of sketched out here. It's you remember the red arrows? That's the direction from this poset to transfer system. The map back is you take the span of the images of the red arrows and then work your way back.
Can I also like this IG and transit?
Yeah.
They somehow like a G fixed point on the poset with a G action. Because are there sort of interactions between the different subgroups with IG and so on?
Yes.
In this
So if
case, your first slogan seriously
Yeah. No, I appreciate that. Yes. Let me think about a better way to answer your question. Thinking about what happens as the group varies over the subgroups is really fruitful. There's a restriction down to the subgroups that has both adjoints. Making sense of that is really productive. The conjugation condition, the second one, is telling me that I really could have had the structure without this, and then there's a G action on that poset, and this is the fixed points of the G action on that poset. So, yeah. All right. Well, here's the punchline, that if I take the left-hand side is the infinity category spanned by the n-infinity operads and operad maps, then the assignment that took my n-infinity operad O to its diagram of admissible sets, that actually gave me a fully faithful embedding. So that any map of the derived mapping spaces between two n-infinity operads is either empty or a point, and it being either empty or a point is perfectly reflected in the corresponding combinatorics. And this is all Andrew and I were able to show. And then Bonavante Pereira, Gutierrez, White, and Rubin all independently came up with ways to show that in fact every indexing system, or equivalently every transfer system, is the index or transfer system associated to one of these operads. So there's no difference between talking about n-infinity operads and talking about these corresponding combinatorial objects, transfer system. So you see a lot of sort of discussion where you sort of play back and forth and blur the line. It's because it's a perfect dictionary between them. I don't know what's next. I'll say that for tomorrow. So I'll stop here.
So will you be considering other types of equivariant operads that aren't like n infinity?
Not really.
Okay. I was gonna ask just like a question about like kind of a moral, like, so for n infinity,
Yeah.
you have this like contractibility
Yeah.
and freeness, but like
Yeah.
for a general operad, you're
Right.
not gonna have like sigma freeness. And so it's maybe
Yeah.
a little weird to consider just the graph subgroups, because you might
Mhm.
want to say, oh, sigma
Mhm.
n, like, is an interesting group and we're doing that things equivariantly, like,
Right.
is it correct in equivariant land to kind of treat sigma n very differently than the group?
That's a great question. And so first I'm gonna punt and say, I don't tend to like using the word correct, because of course,
Mhm.
math is like a cultural product, so we get to make choices about how we're going to do this. And one of the ways I think about this sigma n free condition is sort of from the model category perspective.
Mhm.
It's kind of a covibrancy condition, that essentially one of the things that's easy for me to understand is what do the sort of balance products of the form sigma n cross over sigma n with something look like. So there's sort of the most boring versions of the orbits. If sigma n is acting freely, and this is true non-equivariantly or equivariantly, and I write down some cell structure, then the corresponding cell structure that I wrote down is built out of pieces that look like either the Cartesian powers or the twisted Cartesian powers. It's not built out of pieces that look like the symmetric powers. And those tend to be harder to work with. So I want to make things as easy for myself as possible for this. If I'm the standard model structure, and like Android did all this using models, the standard model structure actually also folds in that the covariant things have this free
Mhm.
action. So any more detail, I'm actually gonna punt to Mike Mendel for, because he foolishly sat in the front row. And literally any kind of question, sort of more technical that he's the one I would go to.
Okay. Thanks.
Yeah.
So, don't really know the stuff, but am I right to imagine that somehow n infinity things are most precisely like EV operads where V is the permutation representation?
I'm so glad you asked. Okay. This one is little disks on infinitely many copies of the trivial representation for CP squared. This one is little disks on infinitely many copies of the regular representation for CP squared. If I'm looking at P bigger than 3, or actually even bigger than 2, because I'm doing CP squared, this is also little disks on infinitely many copies of 1 plus the rotate by e to the 2 pi I over p squared. This one is also little disks on some representation. It's essentially, it's a little harder, but it's also little disks on some representation. This one is little disks on the regular representation for CP squared mod CP. And then this one is not little disks on anything. This one is linear isometries on a trivial thing. This one is linear isometries on a trivial thing, or on the same thing that this is little disks for. This is linear isometries for the same thing as little disks for. This is the linear isometries for this one. So when I build this in a nice way, as little disks on something, this is the corresponding linear isometry. And so that was actually, that observation, I'm really glad you asked this question. That observation is actually what led to all of this. That Andrew and I were thinking about this, and it was like, and studied this universe, and then realized that the little disks on it and the linear isometries on it were different. And that's very, very surprising, because if I'm non-equivariant, there's no difference between the little disks and linear isometries. They're both models for E infinity. And so I thought going into this, oh, it must be true that I see the same thing. How does this all play out? And here, that's where the admissibility condition is really harsh for linear isometries, much less harsh for little disks. And so here, and this is also essentially the last case where they're all modeled by either little disks or linear isometries. But once you get beyond this, then you see things that are either.
Any other questions? All right, so we should have a coffee break now, and the next talk will be at 11. Let's thank Mike again.